And then if you want to stay,
Of course.
Hello.
That's right.
if you want to stay in the camera, it should be staying.
Yeah, I'll stay.
You could quite like a faculty meeting.
Yeah. Okay.
Yes, yes, that's what we do. We do entrance control. You make a picture now, right? And then so you didn't come to the plenary after. Yeah. Maybe we wait 2 minutes.
Sorry,
Well,
now we have to wait.
I mean, they just ate risotto in the sun. What do you want, right? With wine. I probably wouldn't have showed up either. So.
The problem is, classically nowadays we are not used to wine during our journey. You have to be Italian or French.
That's true. Well,
Appreciate that.
definitely true for me.
Or Brazilian.
The risotto didn't help either. And then the ice cream.
Let's have a look outside.
Mike, I'm in practice. What direction is that shot?
Identify buildings. That's, I really don't. That's building 131 right over there. You can see by that big drop tower. Yeah. So
It's the shopping center.
it's a shopping center.
I probably wouldn't recognize the place.
No, you wouldn't recognize it.
I remember that I once went there because it's sort of, if you come from Berkeley, either you go to that one or there's another one in the north, right? We're shopping.
Yeah. There was nothing there back then, probably either.
Okay, I think we should start. So, welcome to this afternoon session. My name is Peter Riggers. I have the honor to chair the talk of Mike Puso. Probably many of you know him from the papers. He was, as I said this morning already, he is one of the developers of the mortar method, and he is sort of all his life involved in contact mechanics. So it's very interesting to see now what you can tell us about the news and contact.
Thank you very much. Thank you, and thanks for inviting me. Thanks for arranging this great conference in this great place with this great weather. So, I mean, really, I don't like the title, but basically, I'm going to give my code developers. I lead a code group, and I support code groups that do contact, and really the better title would be Contact Challenges, Opportunities, and Growth Areas Within the Current Technical Landscape. So just for fun, I'll look at some trends over time in the computational mechanics, contact mechanics arena, look at where the current trends and where the contact mechanics may fit into these new situations. I'll try to put in some context, some recent work in progress. But for the most part, I was doing that work anyways. So back in the good old days, we had these pioneers. They were working on the analytical solutions, which led to the numerics works that many of us have read their papers and really enjoy the books that come out of that. And those were good times. And then pretty soon, transitioning right into the end of that period, computers really took off, and I lived around here. And around the same time, there was this little triangle here between Cal, Stanford, and the lab where I'm from. And Bob was working with some of our favorite people here, and Juan and Todd and Tom, and they basically also consulted for John Hirth-Wyss, who developed the Dyna 3D code. Now, Bob was working on FEEP, and John, from the Dyna 3D code, was basically the first crash code, okay? And that also led to this LS Dyna code. And Bruce Engelman, who worked shortly around that time, take a lot of his knowledge from this code here, Dyna 3D, and helped develop, or mostly developed, Abacus Explicit based on that model, okay? And LS Dyna has kind of an interesting evolution. Dyna 3D was like an open source code for the term open source even really was around. And so for nothing, John took the code and started LS Dyna, got a good return on his investment when he sold it to ANSYS, and then that all blew up quite well for everybody. Paradigm was a parallel, first distributed memory parallel code that I think most people knew about. I showed up shortly after this got started, helped couple to these codes, L3D, OpenFOAM, HyperSolver. Lido is the optimizer. Also have some routines in MFEM. And next, after the 80s, the 90s showed up, and things really expanded really fast. We had representative conferences in contact that we all enjoy, and so many new things really started, popping up. Too many people to mention in that arena, and then the situation on the ground. Now, well, everybody knows you got this runaway AI train, you got GPUs popping up, and you have digital twins and 3D printing. The amount of investment in these areas are huge. These are essentially planned, by the government spending all this money on new chips, and much of it on GPUs to basically run the AI in these data centers. Now, digital twins is something that a lot of people want to do, not necessarily me, but it's an industrial trend that makes digital replicas of physical systems, okay? It's got 3 pillars: digital thread, and that basically tracks parts through sensors. Enterprise software catalogs all the data, and then you set up rules for data governance, determines access and retention, and then there's modeling and analytics, and they use these autonomous AI agents to run either surrogates or finite element models, and account for service history and aging, and then you look at the decisions, look at the risks, so on and so on. And the commercial codes have got into that, and Abacus has virtual twin experience. As Twin Builder, this is their enterprise software, this is their AI agents. And then finally, additive manufacturing, which I've also combined with design optimization to help design parts and engineering materials. You have direct ink printing, you have laser powder bed fusion. There's a lot of methods to do this. Okay, so where does this fit in? Well, this whole thing is sucking a lot of money away from computational contact, computational mechanics to some degree. Project managers often feel that computational mechanics is mature, and I would say not enough. Like for instance, I have a developer we work with at IBM, and he was in the math department writing solvers, and all of a sudden IBM said, we're going to shut the math department down, you're going to go to AI. So I guess they don't need math anymore, they just can use AI. But we still need codes for forward models, for surrogate training, optimization. If you've got an AI agent running ensembles of calculation, you really want a robust code, right? Because contact is very not robust often, and contact is also the bulk of the user support calls. So, and contact is also very hard to optimize on GPUs, and you really want to have some sort of scalability for running these things. You have AI tools such as Codex and Claude, and they don't develop new algorithms, but they help with programming. So contact poses the bottleneck for this new paradigm. Additive matching foams, for instance, encounter self-contact. Design optimization is difficult with contact, so on and so on. So challenges, getting accurate solutions reliably at scale is still a great challenge with contact. Still need to develop new methods. AI is not going to do that for you now. So I need to make my pitch to managers to get money, as other people do in academia. So again, the new paradigm emphasizes robustness and speed, accuracy, and computer within a multidisciplinary environment, because we have a lot of different people from different physics also working on it. And so these are some current work in progress that we had that contain some of these elements. So some linear and nonlinear solution approaches for contact, some geomechanics, some implicit contact dynamics, optimization, and mechanical characterizations. So I'll show some examples. So as Vincent Acari was showing the other day, he was using IP method, basically minimizing, well, in this case, he couldn't minimize the function because he threw in some friction. We got to that point for this, but nonetheless, we wanted to be able to solve these IP type problems or even some homotopy type problems. So you minimize this energy with respect to, say, the gap constraint. Okay, in IP, what you get is you get some, stiffness matrix due to the elasticity. And then what's a little bit different is you have this slack variable, okay? And these are just the constraint matrices. And ultimately, you want to make the slack variable go to 0, because when it goes to 0, your constraint's being enforced exactly, right? But this D gets bigger and bigger as you get closer to S. Basically, this D gets bigger according to some central path. And when D gets really big, S goes to 0. Okay, but if you want to solve this iteratively, that's a big problem because that D gets really, really big. Okay? And you can take that system, and since D is diagonal, and come up with this primal only system. So what happens? I got this dumb, toy problem. I'm solving it, and the optimization steps is going through the central path, making D get bigger and bigger. And if I just use a regular AMG PCG method, I get some number of iterations just blow up. I mean, just blow up. Whereas with the new approach, we get effectively a constant amount of iterations. And if you look at the condition number of that D, it goes through the roof, okay? Like 16 orders of magnitude, okay? So big problems there. So we must be doing something right? So how does this thing work? So say I have some system like this. These are two spheres nested with a beam on top of it. The green is where the contact nodes are. What we can do is just organize them so that this AW basically has all the contact degrees of freedom in it, okay? Now, the way AMG works is you have this V cycle. So if you had a residual here starting, you hit it with, say, Gauss-Seidel or something as a smoother, and then you restrict, either by geometric multigrid or algebraic multigrid, do the restriction down to a coarse solve, and then prolongation, and then get a new ultimate displacement. E is the delta U that comes out of there, and then you would do that and get another search direction from your Krylov solver. That is, but that didn't work just by itself. So they put this filter in here that basically now M is your preconditioner, and you hit your residual here outside with what amounts to being this. But now when you hit the middle term, this AW you can invert this. This is invertible. So you do that with a direct solver, okay? And it's very, very coarse. I mean, very, very, very sparse. It's 2D surfaces, not a large bandwidth, okay? Because it's just nodes on the surface, and then you push it all the way through. After that becomes your full preconditioner, okay? So there, you can show that there's this rigorous bound that if you just had, say, no contact in it, you'd have B. That B is like an AMG B. And there's this idea of convergent solvers using these L1 special types of Gauss-Seidel approaches. When contact's not active, you can show that you get this beta term, this bound, which by virtue of this bound, you can show that you get convergence. Well, basically, you could bound your condition number on that. Well, with contact, with the new approach, with the filter, you get something that looks like this. This is the condition number of this should be close to I, right? Close to 1, and it's bounded by 2 times beta. Okay, not so bad. D doesn't even show up. So that's the upper bound for that. So that's a nice thing to have in your pocket. Okay. So now, we recycle test problems all the time. And here's another silly one with the ironing. We have coarse mesh to fine mesh. This is 317 million degrees of freedom, which is a little bit of overkill, right? So here's the number of potential contact nodes. This is the average ones that are active. This is the number of iterations in your IP solver, and the number of times you go through the optimization. So the conversion 21 iterations, and these are the average number of iterations of your iterative solver. And then this is the upper bound. Okay, so it scales okay. I mean, it's not perfect, and there's a number of reasons why. But 195 iterations for 317 million degrees of freedom isn't too bad. And here's another problem. You have a beam in those spheres, as I showed you, and you push down, the spheres buckle. And now, if you have 70,000 degrees of freedom, or 7,000 degrees of freedom, all these little dots are different time steps, okay? And then this is 190 million degrees of freedom for the fine mesh. And this is the number of iterations for basically 6 time steps that it did. And these are the optimizations. This one, conversion 32 optimization steps. These are like 16. So that went up. But the CG iterations are not too bad. So it does pretty well on that front. Okay, so now we have a code Geos that I consult with on. And it's basically built around GPUs. This code is new, okay? It's nice to have a new code if you want to code on GPUs. So it has multi-phase thermal flow, porous media, faults and fractures and slip, the kilometer-sized domains, okay? Frictional contacts essential for reliably assessing the risk of fault reactivation, induced seismicity, and so on. This work was funded partially by Total and Chevron, supposedly to do carbon sequestration, but I think really what they wanted to do was fracking. These are plumes. These are the faults. They have a typical kind of mesh, and the way they do the contact or the areas where the fluid meets in the cracks, they have standard low order elements. They have finite volume for the fluid flow along the surface, pressure here, and then you do the standard finite volume. The pressure's at the center, so they wanted piecewise constant pressures in the elements. But to do that, they had to put in bubble functions, at least for the elements on the surface, just to keep it stable. And so that all works pretty good, and much of that is in this paper. So this is an example real-world site that they had. These are some of the plumes that you see. This was done on Frontier. This is the second fastest supercomputer. It wasn't 2 exaflops; it was 2 petaflops. That's a typo. And then we look at the scaling, and this is just for the solid part. This is the fluid part. In this case, they did it staggered with an iteration. And so if you look at the say hypersolve, It's not bad. This goes from 20 million elements to 81 billion elements. And things seem to be, but again, this is no contact. This is cheating. And then the whole entire code, it's not that bad considering 8 seconds for an iteration on 81 billion elements, okay, or degrees of freedom. So now let's put some contact in it. And so in this case, you have this fault, and we ran it with, this is what it looks like. There's a reservoir, there's some fluid in some areas that are dry. So where there's dry, you're going to get regular contact, unilateral contact. The contact pressures are 0, the fluid pressures are 0. And now we're doing this on a different machine. The guy couldn't get the GPU part of Geos, not the solver, but wasn't working with the contact. Supposedly there's a fix. But now, if you look at the iterations, anyways, we ran from 7 or 9,000 degrees of freedom down to about 53 million degrees of freedom on this, just the basic Linux box with no GPUs. 1 to 29 compute nodes, 121 processors per node. Okay, and if you look at the number of iterations, they're not too bad. They go from 15 to 23 iterations, and the time for the iterations is nothing. Turns out all the dang cost is in the setup. Building that B matrix is a pain, and that's where all the costs live. Particularly doing the communication of that B term, because that's a whole operator that goes all through that B cycle. You bundle all together in an operator. So this one was bad because it turns out that the communication costs were really big because we had small domains, and also they tell me, and I don't know if I believe this, that the communication costs are high on that machine, and I don't know if I believe that or not, but because I thought I had a pretty fast. Okay, so next I was going to talk about something closer to my heart actually, and we wrote a paper on structure preserving finite forms for friction contact. Not that long ago, about a year ago, we extended that to friction. It will work for node on segment or Lagrange multipliers. What time do I get to? Or do I get to, what time are we supposed to go to? Good. Okay. So the mortar projection, the way we set it up, will actually conserve angular momentum and linear momentum by construction. Energy is conserved for frictionless. It's strictly dissipated with friction. And we also eliminate the contract chatter so that it converges nicely and gives us smooth results. And the work of this here is the goal to get improved robustness and dissipated effects for contact with friction. This is important for a lot of problems that we're also interested in. And the frictionless stuff's in this paper, but the friction stuff's not in the paper. We actually haven't finished writing the paper. So the normal contact gap is as usual. You have the shape function, and you have the difference between the slave side and the master side here. And to make things nice, we have a nodal normal, and we use that nodal normal to do the projection on the segments for that node, so that the gap will always be in the direction of that nodal normal. That actually turns out to be very nice for conservation, momentum conservation. Okay, now what do you do with the slip? Well, the naive slip is this. You take some tangents to that, that are in the plane of that from that normal, and you project them against the increments in displacement, but that's not objective. I think most people know that. So then Todd and I cooked up something a long time ago in a paper where you get a slip calculation that is objective, but that won't conserve angular momentum, and I'm not even sure if it strictly dissipates. So we wanted this to basically do the angular momentum. So how did we do it? So what we decided is, well, in the reference configuration, we can compute based on some, say, edges for a very simple case when you have 4 edges, but you can come up with 3, or it's just a general formula for no matter how many edges meet in a node. And you can set up these tangent vectors like this. They're not exactly orthogonal to each other, and basically just have constant coefficients that determine those directions, okay, based on the edges, okay, great. And then you can get the normal from that. And then by using the invariance, these tangents are orthogonal to that gap. As I said, that gap's in the direction of the normal. And so we know that's 0, okay? We know that's 0. So now when we take the variation of that guy, okay, with respect to a rigid body rotation, which means those weights that determine the gap here, you know, those weights don't change, okay? And so when we push this all through, we know what the variation of these tangents are based on these constants, the weights. And then that gives us this operator, which we know is invariant to rigid body rotations. Great, we'll use that operator to come up with our slip. Okay, so there we come up with a slip using this operator, using these mid-steps, and based on this increment. Okay, so does this work for the objectivity? Well, turns out by using these mid-steps that if you push everything through, it's 0 for a rigid body rotation. Okay, super. Let's see. So now if we have friction, the frictional constraints, you have your contact energy that looks like this, and this is what you get some pressure, variation of the gap, and now you have the variation of the slip, which we have to use a metric tensor because they're not orthogonal to scale correctly. Okay, so now taking based on some rotation of the choosing for the variation of the displacement, this thing is in fact 0, as we know. So when we put that in there, we know that this is going to be 0 because we showed that from before. Now let's make the variation be the increment in displacements, and then when we put that in there, well, that's just the definition of the gap, which we also know by here is if we enforce this is the traction. Okay, so having known that, we can take that and calculate this term here and show that, oh, look, it's strictly dissipating. Great, fantastic. And then you calculate the forces that way. Now we wanted to conserve the energy. Well, we're only going to look at energy due to normal contact. So a gap, a node comes into contact here. It has a force resisting it. That's going to typically dissipate some energy. Okay, we can calculate what those velocities are just from the standard mid-step approach. You know, here's your contact force. We get a velocity, but that velocity is not nice. He can oscillate. So what we do is we use that to compute another one that enforces the gap persistency condition. Okay, so the gap velocity will be 0. We take that impulse here, get the new one, and by enforcing, using a Lagrange multiplier, this is all linear. This is not unilateral, bilinear, I guess. And then calculate a new velocity, but this too dissipates energy, it turns out. So we might want to put it back depending on what we're doing, because maybe we want to conserve it. It depends. Otherwise, if we don't care, we don't care, and we just stop there. So now we're putting it back in, and it turns out that you can put that energy back in just with this calculation right here, with another impulse type calculation to get this new velocity there. And if you're using diagonal mass measures, you don't have to. It's actually an explicit calculation. To get this alpha thing, we show it's well posed, so it's not a problem. It never blows up. We call this mid-step PC because it enforces persistency condition and the conservation. Again, this is just the normal contact. So we don't want no contact to cause us any irritation. So no problem, no friction here. There's a break here where we eventually put pressure on it, and then it stops as you would expect. This just keeps going forever. Now, look at the frictionless case at 3 different time steps here. With the mid-step PC, the new stuff, spins up, okay, you get a pressure. Now I apply, I expand, just thermally expand the top ring. The pressure goes up, but then it stays constant as what you want, right? Because it shouldn't change. With the mid-step, without dealing with the oscillations, without enforcing the gap velocity, you eventually develop a bunch of oscillations. It actually gets worse as you refine the step or time step. Now with some friction, the pressure goes up as they spin. It starts to slow down when I put the brake on. We get some minor oscillations here from both approaches. But when I refine the time step, the mid-step PC guys, it's pretty perfectly smooth. But the regular mid-step just still has those same oscillations that you had before, and again, the same problem over here with the finer time step. And then the velocities is kind of the same thing. The velocity should stay constant. There's no friction. You get some oscillations with the regular standard form. Same thing down here. The velocities with friction slow down, some oscillations. And now here we got gravity on these polyethylene discs. They hit, they should wiggle. With no friction, they should wiggle forever. Now we apply some Coulomb friction to the thing, from big time steps to small time steps here. And we see that we actually get some convergence in the energy, okay? And at these two time steps here, they're pretty much overlap. So we'd consider this converged, okay? And so when we look at that, let's see, with no friction, okay, you get a constant energy. With the mid-step, it turns out you don't get a constant energy. The energy actually goes down as, remember, those things hit and they dissipate some energy as they hit. And actually, when they start hitting obliquely, they can actually gain energy. Whereas now when we put in some friction, the mid-step dissipates strictly as we expect, but the mid-step PC. But the mid-step, it goes down too fast for the same reason as the frictionless. And so that's not dissipation due to friction. That's dissipation due to normal contact. I mean, in most cases, you really can't get rid of that unless you do something, extreme like we're doing here. And so we tried it with explicit, and we get about the same thing. Here's explicit with no friction. This is gray line here. It does almost the same thing. Explicit with friction. It's pretty much the same thing. We get the same answers between our explicit and our implicit codes. Too much dissipation or too fast. So if you're interested in how much dissipation goes in these low dissipation systems, you're gonna need to take care of the fact that you don't want to dissipate just due to normal contact. So now optimization, we beat the heck out of this test problem, right? We want to figure out, I got some volume constraint here on the mass I want to use. I'm going to push this down, and I want to make this as stiff as possible, okay? Or I want to just maximize some contact force. I have this objective function here, which depends on displacements, of course, and this is the densities. This is a method where you can change the density for topology optimization. So you could have some areas like near zero densities and some with densities of 1, which is really, you want something that looks like 0 to 1. And then you could even put the multiplier into the objective function. So we put the multiplier into the objective function and say we want a maximum force given some mass, and that we got something that looks just about the same as if we got the maximum stiffness, it turns out. And this is this paper we published a couple years ago. And so how do you do it? Well, you use the discrete adjoint method. So what you have here is your objective function. You take the derivative with respect to that density, and you get what you see here. And then you get these troublemaker terms, which are basically the sensitivities, the derivatives of the displacement with respect to that density, the derivative of the multipliers, Lagrange multipliers with respect to that density. Okay, so we got to figure out what we want to do with those guys. Okay, so this is an approach that goes way back, but you don't usually see it with other multipliers in it. So here's your residual, as you usually see. You know, we have our Lagrange multipliers enforcing constraints, and we also have the variation of the Lagrange multipliers. Now I'll take the derivative of that guy with respect to the density. So that density that I have here, I just folded it into the energy, okay? That goes away. And then what's left over is all these terms with velocity, or I mean, displacement-related Lagrange multiplier sensitivities. So I add this guy to that guy, right? They're both 0. And then I collect terms. This guy's left over here. But what's downstairs here, I can get rid of. Because effectively, the W and the beta, they're adjoint variables, okay? So I can solve for these multipliers, adjoint variables, to make this whole thing go bye-bye, and then just take this W and put it there. I got this that I will use in either my steepest descent, method of moving asymptotes, or BFGS to do the minimization, okay? And then there's this thing called SIMP, which when you want to basically interpolate your densities using, say, a coarser mesh, and I won't go into this, but if you just use piecewise constant densities, you'll get oscillations. So you got to smooth things out with that. Okay. So now the first thing we optimized was we wanted to have a sabot. A sabot is basically holds in a projectile into a larger barrel, so you can get more force. But we had some volume constraint, and so it also gets very high. Transverse forces. Okay, so it's coming in contact down here per se, and we wanted to do it. So we set limits on, you know, the inside. You know, you got to put a bullet in there, right? So we know what we have to do there. But we also wanted to have some five-fold symmetry. So we enforced five-fold symmetry in the optimization, and having done that, we get something that looks like this. And it turns out you get these on these spokes. They're thinner on the outside and fatter on the inside, and that was the optimal design. But there's also other things called shape optimization. So you get shape optimization where you just change the shape, and you could this is topology optimization that I showed you, and you could actually even do both. Okay. Now you do it with contact. Okay. Say we want to minimize, the displacement of this beam. You have this force on here. So here's the shape optimization. This is the final solution. Okay. And it turned out that it bent things up a little bit, so then it ends up looking like that. This is the topology optimization. It just makes voids. You can't make voids with shape optimization. And then this is doing both. So with both, it gets rid of the material that you don't need, like here. You don't need that, right? And then so you get holes and you get different shapes. And so this is kind of tricky because every node becomes an adjoint variable with the shape optimization. So you have to do some relaxation. You have to put in an energy function into your objective function so that the elements don't invert. Okay. So next, I was going to talk about micro-architected materials. So you have these represented, little units that there's many different kinds, and you can grade them. And we want to build parts that look like this, but even with graded, densities, things like that. There's many different kinds you can choose from. Okay, and so there's ways to do this. We had some representative volumes that you can smush and come up with some types of ways to build this into your model. But they come up with a design. Looks kind of like what we see here. I guess you can't really see it very well because it's shadows, but that's a foam that turns out it was exactly as built from the DIW printer. It has on-machine inspection, so it gives you what it means to be the as-built part that they cut the sample out, because it's pixelated really fine, and then you can build a mesh inside it using tests. And so they want to use that, say, for a potential digital twin. This is their sort of hello world for their digital twins that they want to build at the lab. And so they're starting with some of the polymer parts that they're building. So when we run this in ANSYS, you know, we know what the material properties of all the struts are. It's a polymer. Okay, we ran it now, and in 2 hours, you know, it would get to there, struggle, and that was like one of the better ones, right? But we said, well, you know we could probably run our direct with our implicit codes too, but we thought, I was like, we're going to run with AI agents. I kind of want something that always runs too, and I'm not even sure I trust our codes any better than even ANSYS. I don't know. So then we often use, a lot of these problems use what they call dynamic relaxation. We use it all the time for like metal forming and things like that. And there, if you tune it right and you know what the frequencies of the system, you can do quite well with that. And so now you have the usual explicit time integrator, as you see here. And then when you look at, this is the new inertia, if you look at, minus the old inertia, you can scale that down by a number close to 1 and then run it. And then this thing runs in 25 minutes and goes all the way there. Okay, and this is not a big problem, so you could have got away with implicit. But when we have these problems like this, are 400 million elements, okay, that we built with our, and so we actually can model this one with hexes. So that's what we did. We model it with hexes. And that's a big problem to be running, you can run it, especially if, before everything comes in contact, it'll run okay for sure using the software. But if you, again, want to run this with AI agent, you want to take out one of these struts or something like that, maybe they're aging, maybe they're failing, that's really when the implicit code is going to have trouble. So we have a new machine. This one's faster. The other one was 2 petaflops. This is 2 exaflops. So it's basically 1,000 times faster. And it runs this new chip that they just come out. It's called an APU, which is basically a GPU with unified memory. It's like a CPU and a GPU that they smash together. Okay? And then we have Jane, which is actually a really fast type of HPC computer built on Intel Xeon Sapphire Rapids, which are like some of the fastest. It's a big machine. 11 petaflops is nothing to sneeze at. And the thing is, though, we've tuned the living heck out of codes on these types of platforms. What you want to do when you're doing the tuning is you want to get vectorization. These machines are very good at vectorizing things as long as you maintain cache coherency and take loops that are just big enough so that you don't start thrashing the cache. So you figure out what the loop size is perfect, and then you make lots of loops instead of having one giant one. Well, it turns out that GPU is like one giant one. So how do you mix that in the same code and everything portable? Okay. So then what you start doing is one of the things you have to worry about with GPU loading is a lot more actually than you do with CPU. Right? You have this thing called kernel launch latency, which is like 100 cycles. Now you think, 100 cycles, not a big deal. But on a GPU, in 100 cycles, it turns out there's like 15,000 cores that you can actually operate on a gig cycle on a GPU. Not that really happens in a perfect world. So you better make some big loops, right? So, and then you got to deal with, different kinds of GPU. You got managed memory type GPU, CPU models, which is the standard, and we've got good at. This is rather mature. These are new, and so we've struggled with these. But they have potential to be better because they're unified memory. And the way a GPU works is what they call SIMT, single instruction multiple threads, meaning that, okay, I have what they call 238 compute units. They're actually called streaming multiprocessors in NVIDIA. Okay, this is the last slide, or the next slide. Each unit, you have a wave or a warp. Waves are AMD, warps are NVIDIA. 64 threads on each one of those compute units. During those 64 threads, everybody comes in. It's basically 64 1 through 64 in your loop, 65 through 128, so on and so on. Well, everybody's got to go in lockstep. So everybody's chugging along, and if there's no branches, they're all going to get to the bottom at the same. But if one guy's coming down and he hits a branch, everybody's got to wait till that guy finishes the branch, and then they can move on. So like if you're doing a contact sort, where most things aren't in contact, for instance, everybody's sitting around waiting for that one guy that is doing its work. So that makes things really hard with the GPU to get the most, the arithmetic intensity is quite often not high enough to get the most out of them. And so this is called loop diversion, when everybody's sitting around waiting, tapping their foot. You also, as I said, you had to do loop fusing. So you had to set things up in your code using Python scripts or something to fuse all these loops together, small loops that were in your vectorized code. You want things to be able to work on both vectorization and GPUs. There's all these other mess that you could get into, memory patterns, atomics to get rid of race conditions, and so on and so on. And you want to be able to do all this without killing your performance over here. So right now we've gotten better. We're not there yet. Run this problem. It gives you a good result. But the CPU is quite nice for 12 is run. It wasn't doing dynamically. 12 on Node 3 on Node scale very well. With GPU though on Node, you get 3 times better. You really do at least 5. I mean, that's what everybody seems to be getting. You're not doing contact. To 10, theoretically, you get to 30, and nobody's ever going to get contact. And then you get basically the strong scaling, so you kind of saturation, and that's to be expected, especially loops. If I got the machine, I want to run a bunch of ensembles, right? I really want to pick up one node. So, this guy takes 3 nodes, to get the job done. And at least, so let's just go to, what's the matter? Button. There you go. So just to summarize, AI, we want to, get robustness. We want to get scale. GPUs, very, very difficult to make things portable. Problems with the compilers aren't really all there yet, so we had a lot of workarounds from compilers. Digital twins, who knows? Not a fan, but that's what people are doing. And then optimization, which includes context, which is not brand new, but we're trying to make it actually production ready. So thanks a lot.
Thank you very much. It was a great overview about the current method. We have time for quick questions. Yes.
Thanks, Mike. Very inspiring talk. I got curious about that chattering avoidance technique that you showed. Do you have any guess or explanation why it's so fine when you use that such a particular normal direction? As far as understood, that's the trick, right?
No, the trick is, remember I showed you there's like 3 steps when I actually do the solve. The angular momentum thing doesn't fix it. What fixes is I do the first usual equilibrium solve, and I get a velocity, and that velocity, if I don't do anything with it, could shatter. So what I do is I calculate another velocity that enforces, that's very close to it, that effectively kind of averages it in a way, and it enforces the gap velocity constraint. Yeah. So if I could go back real fast. There, right here. So I get that velocity from this solve here, but this velocity is going to oscillate. So what I want to do is I want to compute a velocity update that's close to this one. Basically gives me the gap velocity being 0. To do that, I compute this impulse equation here to get this new guy, right? That enforces this constraint here. So that guy's constraint is such that the gap velocity is going to be 0. So that guy, the gap velocity is 0. It does dissipate. Well, to be expected, it becomes like a plastic contact. And so, in many cases, you don't even care. You don't want to give it back. You know, you're just doing some system where you need inertia, but you're not worried about the extra damping. So that's how it works. And then again, you can give it back without redeveloping the oscillations.
Thanks a lot. Very clear.
I don't see any more questions. Thank you very much, Mike.